everyone, welcome to Algo-holic, the place where you learn not just the solutions, but the thought process behind solving problems. We are starting off with the most popular problem on LeetCode, the two-sum problem. We are given an array of integer nums and an integer target. We are supposed to return the indices of two numbers such that when we add them up, we get the value target. Now, this is a problem that most people will at least be able to solve using a brute force approach. If not, let me write it down so that it'll help you visualize better. So you have two unknowns and we're supposed to add them up to get the value target. Let's denote the two unknowns by x and y. Now, how many possibilities are there for x? There are n elements in the array, so x has n possibilities. The same thing applies for y. Now, if we were to check each and every combination of x and y, how would that look like? So for x, we run a loop from I0 up until I is n minus 1. Same thing applies for y, where we run a loop from I plus 1 up until n minus 1. All you have to do now is put an if statement inside the two loops to arrive at the answer. Now, what is the time complexity of this? The first loop runs n times. The second loop runs n minus 1, n minus 2, and so on times, which can be simplified to n squared by n by 2, which is big O of n squared. Now, is this the most optimal solution? It's not, but it's a good start. Now, how do you go about optimizing the algorithm? If you look closely, you have two pointers I and j, and at each step we are moving the pointers from left to right. Now, what if we were to start the I pointer at left, start the j pointer at right, and we move them closer? While doing so, we skip certain steps. Now, what steps will you skip? How do you know that you don't accidentally skip over the answer? Because it's not possible to do that without knowing what the array looks like or how the elements in the array are structured. That's when we sort the array, because once we sort the array, we can use the properties of a sorted array to make this decision. I'll show you what I mean. For example, let's say the array looks like this, where we have 2, 5, 10, 25, 50. And let's say the value of t is 30. We'll start up the I pointer here, start up the j pointer at the last index. We'll add them up, we get the value 52. Now, is 52 more or less than t, which is 30? 52 is more than t. Now, if you were to move the I pointer from left to right, we'll get a value which is more than 52 because every element towards the right side of I is more than I. At the same time, if you were to move j pointer from right to left, we'll get a value which is less than 52 because every element towards the left of j is less than j. So we use this logic to arrive at the answer. So we'll move the j pointer, I pointer stays in the same position. Now what is the answer? The answer is 27. Now, if you were to move the j pointer again, we'll get a value which is less than 27. We don't want that. We want to increase it now because 27 is less than 30. So we move the I pointer. I is over here, j is over here. We add the values up, we get 30, which is equal to d. So the values are 5 and 25. Now, is this the final answer? It's not, because the question asks us to return the indices and not the values themselves. Now, when we sorted the array, we lost the indices. How are we supposed to get it back? There's no way to get it back once it's sorted. And the way to solve this problem is, before you sort the array, what you do is let's say the array looks like this: 5, 10, 15, 50, 2, and 25. Before you sort the array, you store the indices in a hash map. So let's say the hash map will look like this, where store the value 5 and its corresponding index: 10 and 1, 50 and 2, 2, 3, and 25 and 4. Now, all you have to do after getting the answer is do a lookup in the hash map table. And what do we get? 5 is here, 0, and 25 is here, 5, which was our answer. So that is 0 and 4, which we got from here, which is the final answer. Now, what is the complexity of this? Well, it takes big O of n log n time, because that is the average time of sorting an array using a efficient sorting algorithm like heap sort, quick sort, or merge sort. The space is big O of n because we need n space to store the elements and its corresponding index. Now, this is a good solution, but can we do better than this? Can we do better than n log n? We can, using two properties here. So one is this equation, and the second is the properties of the hash map. So can you use these two things to arrive at a solution which is better than n log n? What do I mean by that? So in the brute force solution, we assume a value for x, and what we do is we check if that value, if y value exists in the array, which makes up to t. For example, let's say t is 7 and x is 2. What we're doing is we're checking if this value is 7, if this value is 7, if this value is 7, and so on, which takes O of n time. And we're doing this for every element inside the array, while we assume every element as x, which is again O of n. So this is what's happening in the brute force approach. Now, can we somehow shift O of n to O of 1? How can you do that? By using a hash map. Now, what do I mean by that? Let's say x is still 2. Now we know that we want 7 inside the array. Instead of searching for 7 repeatedly, what we do is we store 7 inside the hash map. Now, why are we storing 7 inside the hash map? So that if 7 were to exist somewhere in the middle, when we assume 7 as x, we'll find it in the hash map. So we know that 7 is already a part of an equation, which is the answer. So that's how you solve using the hash map and manipulating that equation. Now, how are you manipulating that equation? If you look at the brute force approach, we are trying to keep this as the equation. Here, what you're doing is we're manipulating that to t is equals to, we're manipulating that to y is equals to t minus x. And t minus x is what's going in the hash map. I'll show you with an example so that it's much more clear. So let's say the array is 2, 10, 15, 25, and 100. And let's say the value of t is 35. So we assume 2 as x. Now what are we supposed to do? After we assume 2 as x, what should y be if we choose x as 2? So we know that y is equal to t minus x. So that's 35 minus 2, which is 33, which is what we are going to store in the hash map. Now, what is the value of 33? We don't want to lose the index, so we'll just store the index. Now, why are we storing 33 in the hash map? We're storing 33 in the hash map so that if we encounter 33 somewhere in the array, we'll know that that is the answer because 33 already exists in the array, in the hash map. So that is the whole logic behind this. Now we store 33 in the hash map. We'll move the x value to the second index. Now 10. Now we'll check if 10 exists in the hash map, as in is 10 a part of an equation. Now 10 does not exist in the hash map. Now we perform this equation again. So 35 minus 10 is 25. We're basically asking what should 10 be added to get the value 35. In our case, 10 should be added to 25 to get the value 35. So the index is 1. Now 15. We're checking if 15 exists in the hash map. 15 does not exist in the hash map. So what should 15 be added to get 35? 15 should be added to 20. And the index is 2. Now we're checking 25. Does 25 exist in the hash map? It already exists in the hash map. So all you have to do now is return the value of 25, which is 1 here, and the index of 25, which is 0, 1, 2, 3, which is the final answer. Now, what is the time complexity of this? We are just moving ones from left to right. So the time complexity is big O of n. Now, what is the space of this? We're just using one hash map to store each and every element. So space is big O of n, which is the most optimal solution. Let's quickly code up the brute force solution where we have I from 0 up until length of array. J starts from I plus 1 up until length of array. Now just check if nums I plus nums j equals the target. Return I and j. So this is the final solution. So that's correct. Now let's look at the second solution where we store the mapping inside a hash map. For example, if you have an array where it's like 2, 3, and 5, in the hash map it's going to be 2, 0, 3, 1, and 5, 2. So now there's a small catch over here because if the array has repeated elements in the hash map, it's going to get overridden. So first it's going to be 3, 0, and it's going to be replaced with 3, 1. So we don't want that. So to overcome this, we store it in an array like this inside the hash map. Now this might seem a bit more complicated, but in an interview, you don't have to come up with this solution. You can just go with the optimal solution. So if value in mapping, so now that it's stored in the hash map, we can start the array. After sorting, we just start off with the pointers, left, right is goes like this. So the left pointer is in the left is in the 0th index, the right pointer is at the last index. While left is less than right, it's not going to overshoot, but this is just good practice. Nums I plus nums j. So if nums I plus nums j is more than target, we are supposed to decrement the right pointer. So lf nums I plus nums j is less than the target, we increment the left pointer. Else we just found the answer, so we can just pop it. Val1, val2 is mapping nums left dot pop, since it's stored in the form of an array. So that's about it. Sorry, this should be left and right. Yep, that should do it. So yeah, the solution works. Now let's look at the most optimal solution. We again have a mapping, and this time we're not going to store the indices, but we're going to store t minus x. So what I mean by that is, let's say we have an array 2, 10, 50, and 100, and let's say the value of t is 60. So when x is over here, we store the value of y. So what should y be when x is equals to 2? Y would be 58, and the indices is 0. When x is over here, we're going to store 50 and 1. X is over here, well, we would have gotten the answer, but if we were to store the answer, it would be 10 and 2. Now here, it's going to be minus 40 and 3. So this is how the hash map would look like. So for index value, the key is target minus value. Now store it in the hash map. Sorry, this is mapping key is value. Now before you store it, we just have to check if it's already present. So if value in mapping, return it, as well as the current index. So this should be the final answer. Just give me a minute. There's a small mistake. Key is target minus value, value in mapping, mapping value index. Mapping key is, sorry, mapping key is the index over here and not value. So yep, this is the most optimal solution. I'll just run it for you. Yep, it's the most optimal solution. So let's look at what the C++ and Java code looks like. So first we have a hash map, we iterate through the array, we get the complement by subtracting value from target, we check if it's present in the mapping, if it's not, we insert it. The Java code looks pretty much the same, where you have a mapping, iterate through the array, get the complement by subtracting value minus target, check if it's already present in the hash map, if it's not, you go ahead and add it. So that's about it. I hope you found this video useful. Your feedback helps me make better content, so please share your thoughts in the comments below. I'll see you in the next video.